the moon is still moving. Not in its orbit, that much we have known for centuries. Moving inside, shifting, trembling. The Apollo seismometers that sat on the lunar surface for nearly 8 years recorded thousands of moonquakes. Tremors emanating from deep within a world that every geology textbook described as cold, dead, and tectonically inert. Those quakes were never fully explained. And now, 50 years after those instruments fell silent, new data from the lunar interior is forcing scientists to reconsider one of the most fundamental assumptions we made about Earth's nearest neighbor. The moon is not dead. It is not even finished cooling. Rafael Garcia is a planetary seismologist at the Institut Supérieur de l'Aéronautique et de l'Espace in Toulouse, France. He has spent years analyzing the seismic records from the Apollo missions and working on the design of new instruments to probe the lunar interior. In 2023, Garcia and his colleagues published the most detailed model yet of the moon's deep internal structure using reprocessed Apollo seismic data alongside gravity measurements from NASA's Grail mission, the Gravity Recovery and Interior Laboratory, which placed 2 spacecraft in lunar orbit and measured the gravitational field of the moon with extraordinary precision. What Garcia's team found upended a decades-old picture of what the moon looks like on the inside. The moon, it turns out, has a solid inner core surrounded by a liquid outer core, much like Earth, a structure nobody had been able to confirm directly until those refined measurements were combined. The solid inner core has a radius of roughly 250 kilometers and a density consistent with an iron-nickel composition. It sits at the center of a world 2,160 miles across, and until 2023, its existence was inferred rather than measured. For most of human history, the moon was understood by what could be seen from its surface. Then, between 1969 and 1972, 12 astronauts walked on it, drilled into it, and left instruments on it. Among the most scientifically valuable were the seismometers placed by the Apollo 11, 12, 14, 15, and 16 missions. For nearly 8 years, these instruments recorded every vibration that passed through the lunar body, from meteorite impacts on the surface to mysterious deep tremors originating hundreds of kilometers below. The data was transmitted back to Earth, archived, and studied. And what it told scientists was deeply puzzling. Moonquakes come in 4 distinct varieties. Shallow moonquakes, the rarest and most powerful, originate at depths of roughly 50 to 200 kilometers and can reach magnitude 5 on a scale equivalent to Earth's earthquake magnitude scale. On Earth, a magnitude 5 earthquake is felt clearly, can crack plaster, and occasionally causes structural damage. The Apollo seismometers recorded 28 shallow moonquakes over 8 years. What made them strange was not their magnitude but their duration. A shallow moonquake on the moon rings for up to 10 minutes. An earthquake of comparable magnitude lasts a few seconds. The moon vibrates like a bell. Unlike Earth's crust, which is saturated with water that absorbs seismic energy rapidly, the moon's dry, cold, fractured crust allows seismic waves to bounce and reverberate almost indefinitely before dissipating. That extended ringing made it extremely difficult to pinpoint where the quakes were coming from. The seismic signals overlapped, folded back on themselves, and frustrated decades of analysis. Deep moonquakes are different. They are smaller in magnitude but far more numerous. The Apollo network recorded more than 7,000 of them across the mission period. They originate at depths of 700 to 1,100 kilometers in the lower mantle, and they repeat. The same locations produce quakes again and again in patterns that correlate with the gravitational pull of Earth and the Sun as the Moon moves through its orbit. These are tidal quakes, generated by the continuous flexing of the lunar interior as the Moon is squeezed and released by gravitational forces. Their very existence implies that the deep interior of the Moon is not a rigid, inert solid. It is something that responds to tidal stress, something that bends. The problem with the Apollo seismic network was its geography. All 4 working seismometers were located on the near side of the Moon, the hemisphere that permanently faces Earth. They covered a region roughly equivalent to Europe. The far side of the Moon, the hemisphere that never faces Earth, the ancient, heavily cratered, geologically distinct half, had no seismic coverage at all. Any moonquakes originating on the far side, or any seismic waves propagating through the deep interior on that side, were either too attenuated to detect or simply went unrecorded. For 50 years, the interior of the far side moon was a seismic blank. In 2024, that changed. China's Chang'e 6 mission, which landed in the South Pole Aitken Basin on the far side, carried a small seismometer as part of its payload. The instrument operated for approximately 14 hours before the lander's solar panels were overwhelmed by the lunar night. In that window, it recorded at least one event consistent with a local seismic source, a small, shallow moonquake originating within a few hundred kilometers of the landing site. It was a brief window, not enough to build a comprehensive picture, but it was the first seismic data ever collected directly on the far side, and it confirmed what theorists had long expected. The far side shakes too. Far more transformative data is expected from the Far Side Seismic Suite, a NASA instrument package slated for deployment on the lunar far side as part of the Commercial Lunar Payload Services program. Unlike the Chang'e 6 seismometer, the Far Side Seismic Suite is designed to operate through multiple lunar days and nights, providing months of continuous recording. Combined with future near-side instruments, it will allow seismologists to triangulate the origin points of quakes across the entire lunar body, including waves that pass directly through the core. For the first time, scientists will be able to tomographically image the moon's interior from the inside out. Garcia has described the Far Side Seismic Suite as potentially the most important advance in lunar science since the Apollo seismometers were switched off in 1977. What do scientists expect to find? The Grail gravity data has already revealed that the crust of the far side is roughly 30 to 40 kilometers thicker than the crust of the near side, a difference that has never been satisfactorily explained and that seismic data may finally clarify. One leading hypothesis for the lunar asymmetry involves a secondary impact, a smaller companion moon that formed alongside the main moon and eventually collided with the far side in a low-velocity impact, piling up its material as additional crust. Another hypothesis focuses on the distribution of heat-producing radioactive elements, which appear to be concentrated heavily on the near side in a region called the Procellarum creep terrain, a vast province of material unusually rich in potassium, rare earth elements, and phosphorus. This uneven distribution of radioactive heating may have kept the near side partially molten longer, allowing lava to flood the Great Basins and produce the smooth volcanic plains called Maria that give the near side its familiar appearance. The far side, cooler and lacking in radioactive heat sources, solidified earlier and preserved its ancient, heavily cratered terrain. But this explanation predicts a thermal gradient that should be visible in the seismic velocity structure of the interior. The Far Side Seismic Suite may detect that gradient, or may find something else entirely. The deep moonquakes throw a wrench into the simplest models of the lunar interior. If the moon were truly cold and rigid throughout, deep tidal quakes should not occur. Rock that is cold enough does not flex appreciably under tidal loading, at least not enough to generate detectable seismicity. The fact that 7,000 deep moonquakes were recorded over 8 years implies either that the lower mantle is warmer than standard cooling models predict, or that it contains partial melt, pockets of liquid or near-liquid rock that allow the surrounding material to deform under tidal stress. Garcia's 2023 analysis favored the latter interpretation. The boundary between the solid mantle and the liquid outer core, the lunar equivalent of Earth's core mantle boundary, may be less sharp than a simple two-layer model would suggest. There may be a partially molten layer sitting above the core, softening the interior and facilitating the tidal flexing that produces the deep quakes. This picture is consistent with a separate line of evidence: the moon's current rate of tidal dissipation. The moon is gradually spiraling away from Earth by roughly 3.8 centimeters per year, a rate measured precisely using laser ranging to retroreflectors left on the lunar surface by Apollo astronauts. This recession rate reflects how efficiently the moon dissipates the tidal energy it receives from Earth. If the interior were completely rigid and cold, the dissipation would be lower and the recession rate would be slower. The measured recession rate implies more internal dissipation than a fully solid moon would produce. Something inside is absorbing energy. And partial melt, sitting above a liquid outer core, is the most physically coherent explanation currently available. The existence of a liquid outer core also bears on one of the most intriguing mysteries in lunar science: The Moon's remnant magnetic field. The Moon today has no global magnetic field. It lost whatever field it once generated billions of years ago, when its core solidified enough that the convective motion driving a magnetic dynamo ceased. But the crust retains patches of strongly magnetized rock, remnants of a field that no longer exists. These magnetic anomalies appear in orbiter measurements scattered across the lunar surface, sometimes associated with unusual surface features called lunar swirls. Bright, meandering patterns that appear optically distinct from their surroundings and align with the underlying magnetic anomalies. The swirls are thought to form because the localized magnetic field deflects solar wind particles, reducing the weathering of the surface material and preserving its original brightness. The question is, what produced those crustal fields in the first place? A core dynamo, running in the early Moon, is the leading explanation. But the timing is contested. Some magnetic anomalies in ancient lunar rocks suggest the field persisted until roughly 1 billion years ago, far longer than standard thermal evolution models predict for a body the Moon's size. If the field lasted that long, either the lunar dynamo operated through a mechanism different from Earth's, perhaps driven by the tidal stirring of a partially liquid core rather than thermal convection, or the magnetization in those rocks has been misinterpreted. The Farside seismic suite, by refining the structure of the lunar core, may help distinguish between these possibilities. There is a broader scientific context that makes the Moon's interior uniquely valuable. Earth and the Moon are believed to share a common origin. The giant impact hypothesis, first proposed by William Hartmann and Donald Davis in 1975, and now supported by a broad range of geochemical and dynamical evidence, holds that the Moon formed from the debris ejected when a Mars-sized body collided with the young Earth approximately 4.5 billion years ago. The impactor, sometimes called Theia, struck at a glancing angle, blasting a plume of molten rock and vapor into orbit around Earth. That material coalesced within decades to centuries into the Moon. Because both Earth and the Moon assembled from the same collision event, from the same mixed reservoir of proto-Earth and Theia material, they carry a shared chemical record of the early solar system. Earth's deep interior, however, is inaccessible. On the deepest hole ever drilled into Earth's crust, the Kola super-deep borehole in Russia, which reached 12 kilometers before heat and pressure defeated the drill, barely scratched the surface of a planet whose interior extends to more than 6,000 kilometers depth. Earth's history has been overwritten continuously by plate tectonics, volcanic resurfacing, and the mixing of crustal material back into the mantle. The ancient record has been largely erased. The Moon's interior has been far less disturbed. It has no plate tectonics. Its surface has been geologically quiet for billions of years in many regions. Its crust preserves impact craters that formed more than 4 billion years ago. In this sense, the Moon is not just a companion. It is a geological archive, a repository of conditions that existed in the early inner solar system before Earth had a chance to erase the evidence. Understanding the Moon's internal structure has consequences that extend well beyond the Moon itself. If the deep moonquakes reflect partial melt in the lower mantle, then the Moon is still thermally active in ways that standard models did not predict. That thermal activity affects the rate at which the lunar interior is outgassing, releasing trapped volatiles from the interior to the surface. In 2015, a team led by Ariel Friedson at the Lunar and Planetary Institute used data from the Lunar Atmosphere and Dust Environment Explorer to detect a tenuous but real helium atmosphere around the Moon, varying with temperature in ways consistent with thermal outgassing from the surface and possibly the interior. If moonquakes and tidal heating are driving more outgassing than previously thought, the composition of the lunar environment near the surface, including the distribution of volatiles in permanently shadowed craters near the poles, which are targets for future human missions, may be more dynamic than static models suggest. If the lunar dynamo persisted far longer than thermal models predict, it implies that something, most likely tidal interaction with Earth, was sustaining the core's convective motion billions of years after standard cooling should have shut it down. That mechanism, if confirmed, has implications for other tidally heated worlds across the solar system. From Jupiter's moon Io, which is tidally heated to the point of continuous volcanism, to the potentially habitable subsurface ocean of Europa, whose internal heat budget depends critically on how efficiently tidal energy is dissipated in its interior. A better understanding of how tidal forcing drives interior dynamics in the moon provides a calibrated laboratory result that can be applied to these more distant worlds. And if the origin of the moon through a giant impact is confirmed in finer detail by seismic imaging of the lunar core composition and structure, it will refine our understanding of the conditions on early Earth immediately after that impact. The first few 100 million years of Earth's history, the Hadean Eon, left almost no geological record on our own planet. But the moon, assembled from the same material, may carry that record locked inside it. The picture is not complete, and the honest state of the science demands saying so clearly. The giant impact hypothesis, despite its broad acceptance, has a significant unresolved problem. Earth and the moon share nearly identical isotopic ratios for oxygen, tungsten, titanium, and several other elements. If the impactor Theia were a foreign body, formed in a different part of the solar system with a different isotopic fingerprint, we would expect the moon, which is thought to be largely composed of Theia material, to differ isotopically from Earth. It does not. The isotopic similarity is almost too perfect. Some researchers argue that Theia and the proto-Earth happen to have the same isotopic composition by chance, having formed at similar distances from the Sun. Or others propose that the impact was so energetic that it homogenized the material, mixing Earth and Theia into a single isotopically uniform reservoir before the moon condensed. A third possibility, proposed by Sarah Stewart at the University of California, Davis, involves a different impact geometry, one in which the impactor was itself massive, spinning the entire system into a rapidly rotating disk that then condensed into a near-Earth composition moon. Each of these scenarios makes different predictions about the structure and composition of the lunar interior. Seismic imaging of the deep core may eventually distinguish between them. The source of the shallow moonquakes also remains unresolved. Unlike deep moonquakes, which correlate clearly with tidal stress, shallow moonquakes show no obvious periodicity linked to the lunar orbit, and their mechanism is not well understood. One possibility is that they represent continued shrinkage of the lunar crust as the interior slowly cools, the contraction generating stress that eventually fractures the brittle crust. Images from the Lunar Reconnaissance Orbiter have revealed thousands of lobate scarps, low ridges formed by thrust faults, distributed across the lunar surface, including on the far side. The geometry and freshness of some of these scarps suggest that the faulting that produced them may still be active. In 2019, Thomas Waters at the Smithsonian National Air and Space Museum led a study that identified 8 shallow moonquakes from the Apollo seismic record that occurred within 30 kilometers of young fault scarps, a proximity statistically unlikely to be coincidental, and the moon may be literally cracking, slowly, as it cools. There is one more line of evidence that does not fit neatly into any existing model of the lunar interior, and it has received far less attention than it deserves. In 2023, a team led by Matthew Siegler at the Planetary Science Institute in Dallas identified a thermal anomaly on the lunar nearside using microwave data from the Chinese Chang'e 1 and Chang'e 2 orbiters. Buried beneath the surface of a region called Compton-Belkovich, an area previously identified as a volcanic complex from orbital imagery, they found a region roughly 50 kilometers across that registers measurably warmer than the surrounding terrain. The heat source is most likely a large body of granite sitting close to the surface. It's still slowly radiating the residual heat of its formation more than 3.5 billion years ago. Granite is a rock type intimately familiar on Earth, where it makes up the cores of continents and forms wherever water and plate tectonics allow magma to differentiate slowly over millions of years. On the moon, granite should not exist in large quantities. The moon has no plate tectonics and is thought to have had very little surface water. Yet here is a granitic intrusion the size of a mid-sized city, buried under the lunar crust, still warm. Siegler described the finding as resembling something we would see on Earth, far more than anything previously detected on the moon. It raises a question nobody expected to be asking. Was the early moon wetter and more tectonically complex than we have assumed? Yet there is something quietly extraordinary about what science is now doing with the moon. We sent human beings there half a century ago, planted instruments, collected rocks, and came home with an understanding we thought was nearly complete. We described the moon as dead. We moved on. And then the instruments we left behind kept talking, in data archives, in reprocessed seismic records, in gravity measurements taken by two small spacecraft chasing each other around the lunar surface. And the moon kept revealing complications we had smoothed over in our haste to call it understood. The moon is not what we told ourselves it was. It has a layered interior more complex than our models predicted. Its core is still liquid in part. Its deep mantle responds to gravitational stress. Its crust is still cracking. Its surface chemistry is being shaped by magnetic ghosts of a field that vanished a billion years ago. And its far side, the face we never see from Earth, the ancient terrain that has absorbed impacts since the early solar system formed, has never been listened to seismically, not once, until now. The next decade will produce the first complete seismic portrait of the entire moon. When that portrait is finished, we may find that the most important thing about the moon is not what it tells us about itself. It is what it tells us about the world it formed with. The history Earth has spent 4.5 billion years erasing is preserved, in fragments, in the rock that orbits above us every night. We just have to learn how to read it. Every generation of scientists has looked at the moon and concluded they understood it. Yet every generation has eventually been corrected. The Apollo era produced rocks, seismic records, and a model that seemed comprehensive. Decades of orbital missions refined that model and filled in details. And now, the details are forcing the model to change again. The moon keeps offering new information. The question has never been whether the moon has more to tell us. The question is whether we are willing to listen carefully enough to hear it.